Today we're going to talk about logarithms, which in the familiar form is looking like this. And this parallels to something I'm just going to write on the board before explaining it, something like this. This is an exponential, this is a log. However, if we plug in the exact same b, the exact same x, and the exact same y, they both represent the exact same things. So you may think about a log like this, exactly like this, and a way to memorize this is with a swirl like this. That's the easiest way to memorize it, meaning that b to the power of y equals x. Another thing how you can memorize a log is that the answer of a logarithm, that where the equal sign is, it will always be the exponent. So y will always be the exponent. B right here, the smaller number that's written in the logarithms, will always be written as a smaller number, and it's underneath the number that it's next to, just like in a normal exponential equation. So you can memorize it that way, and x will just be what's normally the answer of the exponential function will be right here in the logarithm. So that's the explanation of what a logarithm actually is and how you can memorize it. So to give you a real world example to help you guys understand what this means is 2 to the power of 4 equals 16. 2 times 2 times 2 times 2 equals 16. But you can also write this like this. Log 2 of 16 equals 4. Meaning that 4 is the exponent, as I explained before. 2 is what you're putting the exponent to get this big number right here. Or in other terms, you do the swirl like this, 2 to the power 4 equals 16. So that's the definition of a logarithm. That's basically what it is. And in today's video, we're going to talk more about definitions, forms you'll see logarithms in, ways you can use logarithms as well, and properties of them. So the first thing I want to jump into is b to the power of log b of x will always equal x. And in the same way, log b of b to the power of x will also always equal x. Now just to give you a little bit of proof about this, if you don't buy it, let's say b is 2. So log 2 of 2 of, and let's say that this whole thing is 8. So, and we're trying to find what it equals. Well, you can rewrite 8 as log 2 of 2 to the power of 3 equals question mark. And if you take out the log 2 and 2, then you're left with the answer 3 using the properties that I listed above, right? Because this is a 2, this is a 2, this is a 3, and thus this must also equal 3. So then it would log 2 of 8 will equal 3. So that's how this property makes sense. Now you can see many applications of this property in normal problems, such as this. Log 2 of x equals 5. Now this might seem weird at first, but then you can put in a 2 to both sides. This is a rule that you're allowed to do. So you put 2 to the power of everything in these equations. But then you realize that these two cancel out by this property right here. And so you're left with x equals 2 to the power of 5, which means that x equals 32. So that's just an application of this property that you might want to know. And this is a very common property that is used when you're solving equations very, very often, because often you don't. X is used as a number that you're trying to solve for in the equation. And so now we're going into a very common way that you'll see logs written in, and that is ln. This stands for natural log. So this is a natural log. And it might seem weird seeing ln of x, but just know that ln of x is just log e to the power of x. And e is just like any other number you use for logs for. So for example, log 2 of x, you already know what that means, right? 2 to the power of something equals x. Log e is just meaning that log e to the power of something equals x, and e is a constant that's defined by 2.718281 and so on forth. And this is a very common number that's used in log equations. The second way you'll see logs written that might be slightly confusing to you is just log of x. And typically they assume that this means that log 10 of x. So if there's no base written, just assume that it's base 10. So those are the two ways that might confuse you that's written in common mathematics. So now let's go on to some ways you can use logs and some properties of them. So log b of x times y is equal to log bx plus log y. And notice this is converse, so if you have this and they want you to turn it into something that's multiplied by each other, go to this one, and conversely. So just a real world example to explain this one. Let's say you have log 3 of x plus log 3 of 2 equals 2. Now you don't know what log 3 of 2 is because it's some number that you can't really solve for without a calculator. However, you can do this. Log 3 of 2x, because there's a 2 right here, there's an x right here, and they're added to each other, so you can multiply them by each other and put it under the same parentheses, and then the 2 stays the same. So what you can do now is use the thing that we talked about earlier and put both 3 to the power of both sides. So these two cancel out, and you're left with 2x equals 3 to the power of 2, which equals 9. Thus, x equals 9 over 2. And you solve this problem, which was seemingly weird because you don't know what log 3 to the power of log 3 2 is, but then you're able to solve it using this property. So that's an application of this property right here of multiplication and addition of logs. So if we move on, conversely, there's a log quotient rule that states that log b to x over y is equal to log bx minus log by. So this seems familiar to the multiplication one, except that subtraction and division versus addition and multiplication. And in the same way, this can be used in equations. And both of these rules work vice versa. And a lot of teachers say that to compress or expand different types of equations. So I'm going to go ahead and give you some examples of these, and comment in the video below if you think you know the answer to this. So I want you to compress this equation right here. And you can compress this using the rules that we've learned today. Compressing means just like maybe try to put these into one term rather than two terms with a subtraction sign in between. And then expansion, log 8 of 2xy. This is an xy. And then as a challenge, pause the video if you want to try these out for yourself. This one's the hardest one because you have to use multiple rules in order to solve it, and those are log 3s. So just try those, but we're going to move on to a bit of harder rules now that you get the basic rules now. So moving on, we're going to go to an exponent rule. For some reason, when people look at their high school math and think about logarithms, this is the one they remember. And I don't know why they remember it, but it's log b xy is equal to y log b x. So basically this exponent right here, you bring it down to the front and you multiply the whole logarithm by y. That's one that a lot of people remember. Another one, if you're solving like complex equations and you don't know where to start, is the inverse law, which states that log b of c is equal to 1 over log c of b. So basically you just switch the terms and then make it an inverse. And an application for this that a lot of people don't know about is that, let's say you have this equation, log x3 equals a number. And you don't really know because log x is the base in this equation, and it's kind of hard to solve things using bases. It's also hard to have a log under the inverse. So what you would have to do is you can actually flip this, so log 3 of x equals something, and this makes it a bit more manageable. The log is not in the denominator of an equation, and the x is also not part of the thing that you have to put to an exponent to get 3. So that makes things a little bit easier for you if you're trying to solve an equation. So that was the power rule and the inverse rule. Now if we move on to some other rules for you calculus students out there, how do you take the derivative of a log? So let's define f of x as log b of x. Then the derivative of x would be 1 over x times 1 over ln of b. So let's put this into an example because it will probably be easier. Let's say you have f of x, I'll put it over here. F of x is defined by the equation log 2 of x. So log 2 of x. then the derivative of f of x would be equal to 1 over x times 1 over ln of 2. However, that's not all. If you take calculus, you know there's a chain rule. So let's look at a second example of this rule in action. Let's say you have log 7. Log 7, and it's log 7 of x squared plus 2x. You see where I'm going with this chain rule? So 1 over x squared plus 2x. This is considered one entity because under the rule, it's just x. Whatever's in the parentheses is considered x. And you have to multiply this by 1 over ln of x, because that's the rule. But then you also have to do a chain rule of 2x plus 2 multiplied against all of this stuff as well. So that's a more complicated version, and that's about one of the more complicated ones you'll have to do in high school calculus. So moving on to our next property is, I'm just going to erase this really quickly. So moving on to our next property, so x is undefined when x is equal to 0. Now this makes sense because how can you have a b to the power of y equal to x when if x is negative or equal to 0? Because you can't have anything to an exponent that's 0 or negative, because as you decrease y as far as you could possibly go, if you make this smaller and smaller and smaller, trying to get to a negative number, it'll actually just create a fraction that's smaller and smaller and smaller. So you can never, ever, ever have a logarithm with an answer that's 0 or less. So similarly, 0 can't get achieved. So if you have a limit as x approaches 0 of log b of x, and it's approaching 0 but will never actually get 0, you're always going to get negative infinity because you're trying to get as close as you can to 0. So b to the power of negative infinity will help you get that, because it'll just create a smaller fraction that will never actually reach 0, but it will approach 0 from the right, which is what the limit is. So it will be negative infinity would be the answer to that limit. If we look at another property, log, if we go to this side, log b to the power of b, log b always equal 1, because b to the power of 1 equals b. That's a very simple one. It's pretty common, but it's pretty simple. Another one, log b 1 will always equal 0, because as you know, b to the power of 0, if we use our swirl, b to the power of 0 equals 1 all the time. So if you ever have a log equal to, with a answer you have to get as 1, then the exponent will always be equal to 0. Last one, and before I give you guys some practice problems, is the limit as x approaches infinity of log bx will always be infinity. And that's pretty self-explanatory, because if x keeps increasing, the exponent also has to increase and increase and increase. So on a side note, go ahead and graph log of x on a calculator, and try to think about what will happen to the graph if you don't already know, as you are going to x equals infinity, and try to think about it. Just as a hint, know that it's the inverse of an exponential function, so that should help you a little bit. Now some practice problems. The first one we'll do is log 2 of x plus log 2x minus 3 equals 2. And just take a look at it, pause it, think about it, and then go ahead and solve it. Log 2 of x squared minus 3x, this is using our multiplication rule, is equal to 2. Thus, we have x squared minus 3x equals 4, because we're putting both sides, 2 to the power of both sides. And then if we just solve this out using basic algebra, we get x equals -1 or 4. Now, the second one we'll do is log 3x plus 2 over x equals 2. You can just put both sides 3 to the power of both sides, so you'll get x plus 2 over x equals 9, and I'm sure you could do it from there using basic algebra. I hope you enjoyed this video. Go ahead and graph log x on your graphing calculators, and see you next time.